So we want to go through the solutions to workshop number 5. First of all, problem 1 said for each rational function explain in 1 to 2 sentences what is wrong with the setup for this partial fraction decomposition. So part A, I'm not going to write the sentences, but I will explain it. You can write your own sentences. So for part A, the problem is here. Let's actually make that a little bigger. So for part A, there we go. Good. The problem is here. As we can see, since we have an irreducible quadratic, x squared plus 1 cannot be factored over the real numbers, we would have had to write bx plus c over x squared plus 1. That's the problem. Let's see, for part B, let's see. The issue is that we're missing another factor in here. Since we have a repeated linear factor, in other words, we have a linear factor that's multiplied by itself more than one time. What we have to do is we have to include an a over that factor term for all powers of the factor up to 2, because the highest power here is 2. So the correct decomposition would have been, all right, let's see. The correct decomposition for B would have been a over x plus 1 plus b over x plus 2 plus c over x plus 2 squared. So in other words, that's how you deal with a repeated linear factor. You start with the linear factor itself and just keep going all the way up to its highest power. In this case, that's 2, so there's nothing in between. There's nothing in between this to the 1 and this to the 2. But if we had, let's say, I think like we saw in the lecture video, if we had, let's say, x plus 2 to the 10th, you would have had to do b over x plus 2, c over x plus 2 squared, d over x plus 2 cubed, all the way up to another constant over x plus 2 to the 10th. So in part C, the problem is that the rule is that the degree of the numerator has to be less than the degree of the denominator. And what we can see here is that we have degree 5 on top, and on the bottom, once we multiply everything out, we have degree 2. So although this a over x plus 1 plus b over x plus 2 may eventually end up being correct for whatever we get after we perform long division, what you would have to do actually is multiply out the denominator and then divide x to the 5th plus 1 by x squared plus 3x plus 2. That's when you multiply out the denominator, that's what you get. You'd have to perform this long division, giving you some polynomial on top. You'd get x cubed plus dot dot dot, and then plus some remainder. You would then take that remainder and put that over x plus 1, x plus 2, and then you do partial fractions on just this part of it. Here, what you'd end up with is a polynomial that would form part of the integrand once you reduce it in that way. Okay, so that's it. Of course, we weren't asked to solve them; we're simply asked to say what's wrong with them. So in part C, the issue is that the degree of the numerator is not lower than the degree of the denominator, and it has to be lower. So okay, there's the issue there. Okay, so let's do this problem here, where we want to do is write the correct setup for parts A through E, and then finally evaluate this integral down here using what we've learned about correct setups. So for part A, what we have is we have a linear factor and an irreducible quadratic. So the correct setup is going to be a over x plus 1 plus bx plus c over x squared plus 2, and that equals 1 over x plus 1, x squared plus 2. So that's the correct setup for A. For part B, we have, don't be fooled by the fact that this is an x squared. X squared is a repeated linear factor. It's not an irreducible quadratic factor, because of course you can factor x squared by simply factoring it into x times x. So as you can see, it's actually just a repeated linear factor that looks like that. So don't be fooled by that. X itself, without being x squared by itself, without being, like, say, x squared plus a positive number, is a repeated linear factor, not a quadratic factor. So this is going to be a over x plus b over x squared, because that's how we deal with repeated linear factors, then plus cx plus d over x squared plus 7 is equal to 3x plus 2 over x squared plus 7. C. Here we have the repeated linear factor and what looks like a repeated quadratic factor, except it's actually not, because x squared minus 9 is actually just two linear factors. So note that x squared minus 9 is actually equal to x squared, x plus 3, x minus 3, that's the factoring of x squared minus 9, squared. So this is actually x squared, x plus 3 squared, x minus 3 squared. So it's actually just 3 repeated linear factors. The correct factoring is therefore going to be a over x plus b over x squared plus c over x plus 3 plus d over x plus 3 squared plus e over x minus 3 plus f over, I don't need the parentheses there, that's just x minus 3, plus f over x minus 3 squared, and that's going to equal the given fraction, which is x squared, and we now know that should be written as x plus 3 squared, x minus 3 squared. So that's the correct setup for C. Let's, just so we can still see the problems, let's go over here and do D. So D, we have a repeated linear factor and a repeated irreducible quadratic factor. So that's going to be a over x plus 2 plus b over x plus 2 squared. That's the repeated linear factor. Plus cx plus d over x squared plus 5. And then plus ex plus f over x squared plus 5 squared. And that's, of course, just going to equal 3x squared plus 2x plus 1 over x plus 2 squared, x squared plus 5 squared. And finally, e. What we have is, doesn't look like we have anything, since we have what looks like a quartic function. That's the name for a fourth degree function. But actually, if we factor it, what we'll see is that that's just going to equal 1 over, I'll factor out the x cubed, and that becomes x cubed x plus 2. So we actually have a thrice repeated linear factor of x, and then another linear factor that's not repeated of x plus 2. So that's just going to equal a over x plus b over x squared plus c over x cubed. Recall, that's how we deal with a linear factor that's repeated 3 times, is we use all the powers starting at 1 up to the highest power, and then x plus 2 is not a repeated linear factor, so it looks like that. Okay, so that's the answer to E. So now, if you notice this setup, at least the denominator in E, looks suspiciously like the problem that we're asked to actually evaluate there. So now we know how to actually set that up. That's going to be a over x plus b over x squared plus c over x cubed plus d over x plus 1 equals 3x cubed plus 5x squared plus 7x plus 4 over x cubed x plus 1. So I want to solve that. Problem is peeking out from there. We'll do that one next. So I want to solve this for its constants in order to be able to find the integral of it. So let's, since the question does actually ask us to integrate that function, so let us multiply through. It gives us a x squared x plus 1 plus bx x plus 1 plus c x plus 1 plus dx cubed equals 3x cubed plus 5x squared plus, that's 7x, excuse me, plus 7x plus 4. So there we go. And that is now, what I want to do is I'm going to do this by grouping. That's just my preferred technique for ones where we can't zero out everything. So I'm going to multiply this through, and this becomes ax cubed plus ax squared plus plus bx squared plus bx plus cx plus c plus dx cubed equals 3x cubed plus 5x squared plus 7x plus 4. I can now group everything with an x cubed together. That's going to be x cubed a plus d plus x squared a plus b plus x b plus c, and then plus c. That accounts for all the terms, and that's going to equal 3x cubed, 5x squared, 7x plus 4. So the only constant terms are c on the left and 4 on the right, so we know that c is equal to 4. We then know that b plus c, the x term here, has to match this coefficient, so b plus c equals 7. Since we know that c equals 4, that means that b equals 3. Since we know b equals 3, the x squared term is 5, so this has to equal 5. And since b is 3, that gives us that a is 2. And then a plus d has to equal 3, because the x cubed term on the right is 3, so this is going to equal 3. And since we know that a is 2 and a plus d is 3, that means that d is equal to 1. So what we're finding here is the integral of 2 over x, I'm just filling in the constants from the original setup, that's going to be 2 over x plus 3 over x squared plus 4 over x cubed plus 1 over x plus 1 dx. And that's going to be, we can just read these right off, that's going to be 2 ln x minus 3 over x. You can check me on that, but that's the antiderivative of 3 over x squared just by the power rule. And then this is going to be minus 2 over x squared. Once again, you can, I'm not going to go through how to apply the power rule. I know you can do that. And then finally the last one, 1 over x plus 1 is going to be ln absolute x plus 1. And then finally, I don't want to reuse c, so let's just give the constant a different name. Let's call it m. There we go. Don't try that on my lab. My lab is expecting it to be plus c, but for on paper we can certainly write it as plus m. Okay. Next question. For each integral below, identify an appropriate trigonometric substitution and convert the given integral into an integral in the variable theta. Do not evaluate the integrals. All right. So for a, you recall that the rule. I'll just write it out for sine. So if we have something of the form square root, if we have something of the form a squared minus b squared x squared, then we use the substitution a over b sine theta. So here, clearly our a is square root of 5 and our b is 1. So the substitution is going to be x equals root 5 sine theta dx is equal to root 5 cosine theta. So that means that the answer here is going to be this is going to be square root of 5 minus 5 sine squared theta times root 5 cosine theta. I forgot the d theta there, d theta. So that's how we're going to substitute a, and this now is equal to integral of root 5 square root of 1 minus sine squared theta times root 5 cosine theta d theta. But this, of course, is just equal to cosine theta, so this is now going to be, we have here integral of 5. There are 2 powers of cosine, 2 factors of cosine. We have integral of 5 cosine squared theta d theta. All right, now let's do b. So b, we have sort of the reverse situation, although we have a tangent type substitution. Recall that 1 plus the x squared term is going to give us a tangent type substitution. So applying sort of an analogous rule, a squared plus b squared x squared, that gives us a over b tan theta. So here, the b is going to be root 5 in this case. So this is going to be x equals 1 over root 5 tan theta dx equals 1 over root 5 secant squared theta d theta. So once I do this, I'm going to get the integral of, I'm not going to do the whole substitution here, but recall that 1 plus tan squared equals secant squared. So once you do all the algebra, what you're going to get is 1 over root 5 secant theta times 1 over root 5 secant squared theta d theta. So just to be clear, this is the dx part of the original integral, and after simplification, this is the 1 plus 5x squared part, the square root of 1 plus 5x squared part of the integral. So this should equal integral of 1/5 secant cubed theta d theta. And by the way, you should really know how to integrate secant cubed. That's done by integration by parts using u equals secant theta. That's a very, 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 very important sort of integration to know how to do, but I'm not going to do it here because we kind of did it last week with cosecant. Okay, so c, that is, let me just write it out, that's x squared 13x squared minus 5 to the 3/2 dx. So this is going to be a secant type substitution. What we can see is that a is equal to root 5, b is equal to root 13. So this is going to be x equals root 5 over 13 secant theta, and dx equals root 5 over 13 secant theta tan theta d theta. So the integral is going to equal x squared, so that's going to be 5 over 13 secant squared theta. That gives us the x squared that you see there. And then here, once we substitute this, what we're going to end up with is, actually, let me just do it in line. This is going to be 13 times, if I square root 5 over 13, what I get is 5 over 13, and then and then the secant part, I also have to square that, so that's going to be secant squared theta minus 5 to the 3/2. And then finally I have the dx term, which is root 5 over 13 secant theta, tan theta, d theta. There we go. So we just really need to do some simplification here. So I've got the next problem sort of peeking out. I just want to get rid of that for now. So we have is 5 over 13 secant squared theta times 13 times 5 over 13 is going to be 5. So what I'm going to end up with here is 5 secant squared theta minus 5. So to the 3 halves. So I'm going to factor this out. This is going to be 5 to the 3 halves. It's going to be 5 to the 3 halves and times secant squared theta minus 1 to the 3 halves times root 5 over 13 secant theta, tan theta, d theta. There we go. Okay, so what we have here is we have, let's see, 5 halves, actually, let's add up all the powers of 5. So we have 5 to the 1 and 5 to the 3 halves. That gives us 5 to the 5 halves, and then another half. That's going to be 5 to the 6 halves, or 5 cubed. So this is going to equal the integral of 5 cubed, or 125. And we also have 13 times the square root of 13, so that's going to be 13 to the 3 halves, or I could write it as 13 root 13. And then here I have, let's add up the powers of secant. So I have secant squared here, and then secant there, so that's going to be secant cubed theta. This is actually, secant squared minus 1 is tangent squared. So when I raise that to the 3 halves, just note that tan squared to the 3 halves just equals tan cubed. So this is going to be 3 powers of tangent and 1, so that's going to be tan to the 4th theta d theta. I think I've accounted for everything correctly there. That's good. Okay, so there's part C. Now let's do part D, which is the integral of, and by the way, there should have been a dx here. I apologize for that typo in the problem. So it's x squared minus 20x plus 107. So D, we have the integral of the square root of x squared minus 20x plus 107 dx, even though I didn't write it. So the thing to recognize is you're going to have to complete the square with this sort of quadratic. So we know is that x squared minus 20x is equal to x minus 10 squared minus 100. So I can say that x squared minus 20x plus 107 equals x squared, equals x minus 10 squared minus 100 plus 107. So I'm just replacing this part with this expression. And so now I just add that up. That becomes x minus 10 squared plus 7. So here, it's kind of like we're doing like u squared plus 7 with this equal to u. Except I don't really need to do it with u. I can just do this in line. So I'm just going to do, just like I did in the video, I'm just going to write x minus 10 equals square root of 7 tan theta. And the derivative of x minus 10 is just 1. So that gives us dx minus 10. See the lecture video as to understanding why the derivative of x minus 10 is just equal to dx. So that's going to equal root 7 secant squared theta d theta, and that means that the given integral is going to be, let's see, so this is the integral of x minus 10 squared plus 7 dx, which is going to equal the integral of the square root of 7 tan squared theta plus 7, because I'm replacing this x minus 10 with root 7 tan theta, and then dx is times root 7 secant squared theta d theta, and this finally becomes, when I factor everything out, this becomes root 7 and then square root of tan squared theta plus 1 times root 7 secant squared theta d theta, and that equals 7 square root of tan squared theta plus 1 is secant theta, so I have, this is going to be secant theta, and then I have another power of secant, 2 powers of secant, so I have 7 secant cubed theta d theta. Boy, is the knowing how to do that secant cubed really important. So, okay, so there we go. That's the last one. And of course, we don't have to actually integrate these, we just have to set them up. So, okay. Finally, we have number 4. I know this was giving a lot of people a lot of confusion. What could I possibly have meant by this? And one of the biggest mistakes that I saw in this problem is people they actually tried to find lowercase f. They're like, well, how can I possibly do that? How can I ever find the integral of lowercase f if I don't even know what lowercase f is? So they surely figured they had to find it. If you unpack this problem, you realize that this is really just a trig sub problem with the first step done for you. In other words, if I tell you that I want you to find the integral of the square root of 1 minus x squared dx, the first thing you do is you say, Well, x equals sine theta dx equals cosine theta d theta. So this integral, through some magic that we already did, becomes the integral of cosine squared theta d theta after I do all the simplifications. So now you're going to say, oh, okay, well, in that case, I know what it is, except that's not the substitution that I gave you, and it doesn't matter what the substitution I gave you is. In fact, here I gave you a tan type substitution, so this is not going to explain what f was. The point is it doesn't matter. Here, I'll put it in red just to emphasize it. This is f of x. So the original integral was of the form f of x dx. Now what did you do? You converted it into an integral of the form g of theta d theta. So here's g of theta. Now, what do? You find the antiderivative of cosine squared. You go on, you back substitute, and that gives you the answer to the original problem by trig substitution. Well, here all I've done is I started with some function f of x dx, or some integral f of x dx. I did a substitution, and somehow I got to here. So in other words, I've done everything up to here for you and told you whatever process, whatever miracle I had to perform to convert the original integral into a trig integral, I did it already. So what do? You just go on from there. So, oh, and by the way, why is that going to give us the answer? Well, if I'm trying to find the antiderivative of f of x dx, what I know is that that's equal to capital F of x plus c, but let's ignore the plus c for now. So, in other words, that's the relationship. In other words, capital F is equal to the integral of lowercase f is an equivalent statement to saying that the derivative of capital F is equal to lowercase f. These two statements mean exactly the same thing. So in other words, the full setup here is capital F is equal to the integral of f of x dx. How do you know that? Because I told you this. Now, the next step is that this is equal to cosine squared theta d theta. How do you know that? That's part of the word problem. The substitution converted that integral into this one, so that means that they must be equal to each other. Now, we can find the antiderivative of cosine squared theta. That's just going to be the integral of 1/2 1 plus cosine of 2 theta d theta, which equals 1/2 theta plus 1/2 sine of 2 theta, which equals 1/2 theta plus sine theta cosine theta, because sine 2 theta equals 2 sine theta cosine theta. And so that equals, to write it better, write 1/2 theta plus 1/2 sine theta cosine theta. Now, what do? We write the triangle. We're already told what the substitution is. So what that means is that if x minus 1 equals 3 tan theta, then that means that x minus 1 over 3 equals tan theta. So that's x minus 1 and 3. And that means that this is going to be 9 plus x minus 1 squared by the Pythagorean theorem. So our final answer, once we do the back substitution, is 1/2. If tan theta equals x minus 1 over 3, then that means that theta itself equals arctangent of x minus 1 over 3. And then plus, we have sine theta 1/2 sine theta cosine theta. Sine theta is x minus 1 over the square root of 9 minus x minus 1 squared, or plus x minus 1 squared. And then cosine theta is 3 over the square root of 9 plus x minus 1 squared. So you could simplify it a bit from that point, but that's sort of beside the point. Whether you simplify it or not, this is the correct answer. Oh, I forgot, of course, the hardest part of the problem, the plus c. What I find really, really interesting about this problem is if I had simply given you some function and said, here, go perform the recipe for trig substitution, you would do it. If I gave you a 10-step process for finding an antiderivative by trig substitution, you would do it. All I did here is if trig substitution is a 10-step process, basically I did step 1 for you and said, here, go do the process from steps 2 through 10. And just by dropping you into step 2, I found this problem confused so many of you as I watched you do it during the problem solving session. So it's really interesting, but you have to sort of learn to recognize what it is that you're doing when you do these problems, because this was a relatively simple problem to solve once you knew what the antiderivative of cosine squared was, but it was just hard to recognize that you were just basically being given an ordinary trig subproblem with the first step done for you. So okay, that's it.